Okay, so for our assignment here, on uniform circular motion, all right, I posted this, guys, on the classroom. If you click on the link, it's going to bring you to this website, and you can make this bigger if you want. It has these couple different variables set at certain points or certain values. And with this, though, we can kind of vary these up and determine what's going to happen to the acceleration, what's going to happen to the net force. And we can also get a visual of the different vectors involved. So let's just start it off real quick. You see the object is rotating at a constant speed around the fixed center point here. Okay, cool. So if I wanted to know the direction of the velocity vectors, I go over here to vectors and I click on velocity, and you're going to see that. So even though the speed is at a constant 20 meters per second, is the velocity constant? No, because it is constantly changing directions. And again, in order to change direction, you need a force. That force for circular motion is your centripetal force, which is always directed inward. Now, accelerations are produced by net forces, all right, and they have to be in the same direction as the net force. So if the net force is directed inward, you're going to have velocity vectors, your acceleration vectors also directed inward. All right, centripetal acceleration. So the word centripetal means center seeking. So at any given point, if we just pause it here, the acceleration vector is pointed inward. All right, we pause it over here, it's pointing inward. Stop it here, it's always going to be pointed inward. But the velocity vector is constantly changing because it is constantly changing direction. Now, look at the net force. Let me start this up. Okay, cool. What happens? What do you think is going to happen to the force if we decrease the speed? Let's see. Okay, it decreases dramatically. So at 10 meters per second, we're at like 33 newtons worth of force here. If we doubled the velocity, now we're up to about 133 newtons. So changing the velocity is very much so going to drastically change our net force. Now, if we increase the speed again, you can see that it is dramatically increasing. And so is the acceleration, and therefore the force as well. So let's bring it back down to where we were originally.
Is that why, like, when you feel like if you're throwing a ball and you swing really fast and like let go, that it goes really far?
Yeah, it's going to go farther.
Like more force.
Yeah, so like the more force you're swinging it with, the farther it's going to go. Now, if you're thinking about swinging a ball over your head and you have a longer rope, it's going to be a lot easier to swing that. Now, what would happen, though, if you use a shorter rope? Well, look at what happens to the force and to the acceleration. Okay, when you decrease the radius, you're drastically also increasing the net force and the acceleration. All right, so Ms. Mbara, why the hell is this important? Why is this like a big deal? Why is this important? Well, if you're thinking about, let's say, driving, and you're going around a curved bank, all right? Usually they're going to have signs, or pretty much always going to have a sign next to it that says, travel at this speed. Now, there's a lot of physics that goes into that to determine, all right, what speed it's okay to travel at. Pretty much taking the average mass of a car or vehicle and the friction between the tires and the road itself, they're going to come up with pretty much a certain amount of force that is going to be needed. And if the object is going, let's say they say, all right, it's safe to go around this curve at 20 meters per second. But if you go over that, right, if you coming in hot, coming in at like 30 meters per second, now the net force is not good. All right, it's you would need this much net force in order to keep you moving in that curved path the way you already were. So now you're going to wind up skidding out. There's not enough force holding you in place, and you're going to wind up skidding out. So if most of you guys are either starting to drive or got your 6 hours or permits, all right, there's reasons why there are speed limits. So if you coming in hot like that, all right, there's a very high risk of skidding out and sliding. Now, they put the number probably a little bit lower than you can actually go, because they have a feeling like, okay, well, if I say go around this curve at 25, most people are going to be like, all right, well, I'm going to go around it at like 30 or 35. But if they, if going around that curve at like 40 is not good, and you put 40, people are going to go in, coming like probably most of the time going in faster, and that's not good. That's definitely not good. So we're going to pause this for this second. We're going to reset. So if we go back into our assignment itself. All right, part one is pretty much just to go on there and get familiar with the varying the radius, the mass, the speed or velocity there, and figure out the vectors. So that's pretty much what we were doing. So we don't have to actually answer anything for number one. But for number two, okay, velocity is a vector quantity which has both magnitude and direction. So using a complete sentence here, describe the object's velocity. Okay, well, if we look at the simulation, all right, let's put the velocity vector in. Let me just hit start. Now, as this thing is going around, right, if we look at the speed is constant. So is the velocity constant?
No.
No. And the reason why, all right, it kind of even says it right here. Has magnitude and direction. So what you guys would pretty much type in here somewhere along these lines, using complete sentence to describe the velocity. All right, so the speed is constant going around the circle. But the direction is constantly changing. And once you guys write something along those lines, okay, you highlight it and turn it red. All right, so the speed is constantly going around the circle, but the direction is constantly changing, as you can see from the simulation itself. Speed is the same, but the velocity vector is constantly changing. Why is it constantly changing? Because we're constantly changing direction here. So 3 asks, if an object moves in a circle at a constant speed, its velocity vector will be constant. True or false, and explain your answer. Well, we should pretty much answer that. That is definitely false. All right? Because by changing the speed, you're constantly changing direction. I'm sorry, not changing the speed. By changing the direction, you're constantly changing the velocity. So there's going to be a question on your tests on this stuff where it's going to ask, okay, an object moving around in a circular path at a constant speed, is it moving at a constant velocity? And just a lot of people are just going to look at it and be like, real quick, yes, because they just put speed and velocity together. Remember that velocity is speed with a direction. So, and think about a circle. You're constantly changing direction. So number 4, All right, in this diagram that's off to the right, you have a circular path with a couple different points on here. At each of the points, they ask to draw in a velocity vector and an acceleration vector. Now, with this, they're telling us that it is moving in a clockwise direction, so that's important. So if you guys don't feel like doing this on the Google Doc and following along with me, you can do it on a separate sheet of paper. Guys that are doing it with me in the Google Doc. Okay, you're going to click on the picture itself, and you're going to hit edit. It's going to bring you to this. All right, so clockwise, we talked about this before. All right, something that's moving around the way that time would move around on an actual clock, that's your clockwise. So if this is 12 o'clock up top, 3 o'clock, 6 o'clock, time is supposed to go from 12 to 1 to 3. I'm sorry, 12 to 1 to 2 to 3, all right, to 6 to 9, back around. If it was not moving in that direction, we would have it as counterclockwise. But they said this thing is moving around clockwise. So right here where it's that little line button, you go over to the right, there's a little drop down thing. Click on that and you're going to hit arrow. Now, once you do, you're going to go over one of these little, all right, dots here, and we're going to draw a tangent line. So a tangent line is pretty much a straight line coming off any point along this circular path. So I'm going to click on this guy, and I'm going to draw it a straight line out. That's tangent to its path. Now, guys, it's going to not come out perfect, so don't freak out over that. Go to the next point. That's not tangent. This is not tangent. A straight line coming off of that point. Again, don't freak out if it's not perfect. It's not very easy to do on this. But this is how you would do it. At this point, okay, it's a straight line coming off. And you're going to repeat this for all the points. So this bottom one, oops, got something I didn't want there, so I'm going to hit undo. Go back for my little arrow thing. And then my final dot. Okay, these are my velocity vectors. So I'm going to then, after I have all of those drawn in, and it looks like this, I'm going to go to the text box. I'm going to click on text box, and just above one of these, I'm not going to do it for every single one because it's just a pain. I'm just going to type in the letter V for my velocity. Now, the other part of this said it wanted to have us draw in the acceleration vectors. So crap, I forgot what direction the accelerations are. So if I went back to the simulation and click on the acceleration vector, I can see here that at any single point, it's pointed inward, all right, towards the center. Okay, so that's great. So at any single one of these points, now we're going to draw in, all right, our acceleration vector. So if I click on this point, it's going to go directly towards the center. That was annoying, so let me redo that. Arrow. Okay, that's about the center. I'm not going to do it for all of them on this because that's a lot, but I'm going to just do it for like these three over here. All right, so these three pointing inward, those are going to be our acceleration vectors. So once you have those guys drawn in, just go to text box and you can just do it for one of them. That was not what I wanted to do, so let's undo that. Text box. There we go. All right, and then bam, there's our acceleration vectors. Once it looks like this, all right, you can save and close. If you guys did it on a piece of paper, that's fine. You're just going to have to take a picture of it and attach it to this. All right, so describe the relationship between the direction of the velocity vector and the direction of the acceleration vector for a body that's moving in a circle at a constant speed. Okay, so what is the relationship? Well, all right, so the velocity vector is tangent to its path. So it's always a straight line to its path. And the acceleration vector at any single one of those points is directed, all right, the acceleration vector is directed towards the center. And once you have that drawn, or once you have that written in, or something along those lines, highlight it in red, and then we are going to stop there. We're going to stop there for the day. Okay, we'll continue on with the other pieces of this tomorrow. So just leave this here for a second while you guys start typing that off.
Is this how like a rotary engine works? Like it like creates energy by spinning in a circle or something?